Hello everyone, welcome to our presentation on TRON, a solver for trajectory optimization with non-smooth cost functions. This is joint work with Drew Bagnall and we are from CMU. Trajectory optimization is a general framework to synthesize dynamic motions for robots where we seek to minimize the cumulative cost of a trajectory by finding the best control sequence subject to constraints on dynamics. Most existing approaches heavily rely on the differentiability of the cost function and use nonlinear programming techniques to achieve fast convergence. But what if the cost functions are not differentiable? In other words, not smooth. Popular solvers such as ILQR have extremely slow convergence affecting real-time performance. We see instances of non-smooth cost functions in several applications. We give two examples here, one involving collision avoidance in path planning, where the obstacles are encoded using a non-smooth cost function as shown on the left. On the right, we show a surgical application where we desire sparsity in control of a needle that is inserted into the human body. Our work presents a fast solver, TRON, for structured non-smooth cost functions that are composed of smooth components. The non-differentiability of the cost functions arises through the max operator, and the examples discussed in the previous slide conform to this structure in addition to several others. We reduce the problem by ignoring the dynamics constraint for now and working with a simpler formulation as shown in the bottom of the slide. We further reduce it by introducing a dual variable theta which lies in the 2D simplex. We frame this as a two-player min-max game between a player and an adversary. The player tries to minimize a regularized objective in y, while the adversary tries to maximize the same regularized objective in theta. Note that the regularization penalizes deviation of theta from its previous iteration value. Turns out, the inner maximization in theta can be solved in closed form, thereby giving us the simplified objective in y, which is smooth and twice differentiable. Interestingly, the objective adapts to the adversary, and we can observe that we improve the approximation as the regularization coefficient goes to 0. We can apply the same approach to trajectory optimization, resulting in a smooth, twice differentiable objective with dynamics constraints. This can be solved efficiently using any trajectory optimization approach such as ILQR, DDP, etc. Thus, we have a fast iterative solver for non-smooth cost functions by reducing it to a smooth adaptive objective. We test TRON on a motion planning task for differential drive robot with collision avoidance and we compare it with ILQR. As expected with non-smooth cost function, ILQR has extremely slow convergence while TRON quickly converges to a collision-free path. We also tested TRON on the surgical needle application where we desire sparsity in the angular speed of the needle. We compare it with ILQR and a recently proposed ADMM-based approach. TRON outperforms both in convergence and results in a sparse trajectory which is highly desirable in this application. I would like to end my presentation by emphasizing that TRON works really well for trajectory optimization problems with structured non-smooth cost functions. Thank you.